All right, we're back for part 2 of star life cycles. We've already done the red dwarf life cycles in part 1. Now we're going to be doing the low mass star life cycle. This life cycle is important for us because our sun is a low mass star. All right, now, as a reminder, we don't need to do the first 2 stages again because the low mass star life cycle starts with the protostar and main sequence stages, just like every other star. The only difference is because these low mass stars are higher mass than the red dwarfs, those stages take less time than the red dwarfs took to do them. Now, after the main sequence stage, remember the main sequence stage is when the core of the star is burning hydrogen. When the core is fusing hydrogen, we have a main sequence star. That can only go on for so long because eventually this core will run out of hydrogen. As soon as that happens, we move into the next stage, which I'll give you the name of in a moment. The name comes from what happens to the star, so let's first look at what happens to the star after the main sequence, and then I'll explain what the name is. Now, after the main sequence, during the main sequence, the star is extremely stable. Not a lot happens to the star. It tends to have the same size, the same temperature for a very long amount of time. Now, after that core runs out of hydrogen, though, it's going to go through some changes. Specifically, the core size will change, the core temperature will change, the luminosity will change, the surface size will change, and the surface temperature will change. Now, these things will change a lot over the next few stages of the star's life. So I have made a chart here, and you probably should try to make this chart as well. It's a chart that's going to show whether these things are increasing or decreasing. I'm going to use arrows in the chart to indicate increasing and decreasing. An up arrow means an increase, a down arrow means a decrease. All right. I'm also going to draw what's happening in the core region of the star. Now, by core region, I mean the core and the area around it. All right, so let's assume that the main sequence has ended. Now, because fusion is happening in the core during the main sequence, the pressure that's caused by that fusion fights the inward pull of gravity. That's why the star stays very stable. Now, when the fusion turns off in the core, that means nothing is fighting gravity in the core. If nothing's fighting gravity in the core, gravity will crush the core. Now, if gravity crushes the core, what should happen to the surface size? Well, it should be pretty simple to see that the surface size decreases. Now, if we're crushing the core, that means we're crushing a gas. And if you remember, if you crush a gas, it gets hot. So if the core is shrinking, the core temperature will go up. Now, at this point, remember, the reason that the hydrogen around the core was not fusing before is because it wasn't hot enough out there. But if we just crushed the core and made extra heat in the core, then the area around the core can start fusing. So that means during this next stage, the core region is going to have, the core itself is made out of helium, because that's what you make out of hydrogen fusion. And there's going to be a shell around it where hydrogen is fusing. So whenever I draw these diagrams here, I'm always going to write what the region's made out of, or what the area is made out of, as an element: hydrogen, helium. And if a region is fusing, I'll put a little lowercase f. So during this stage, the helium in the core is not fusing, but the hydrogen around it is fusing. This is called hydrogen shell fusion. Now, because our core temperature is now extra hot, and because this shell is actually bigger than the core was, we're actually fusing more now than we were during the main sequence. So that means that the luminosity is also going to go up. Now, if the luminosity goes up, then that means more light is pushing its way out of the star. That's going to push the rest of the gas in the star out. Now, what is that going to do to the overall size of the star, the surface size? Well, it's going to make the star grow. And if we let the rest of the star outside of the core spread out or grow, then that means it's going to cool down. So the surface temperature will actually go down. So I want you to notice something here. The core shrunk and got hot, but the surface grew and got cold. The surface did the opposite of what the core did. Now, these changes are all very extreme. The surface is going to grow to the point where our sun will completely engulf both Mercury and Venus. We won't quite be inside of the sun at this point, but that means the sun is much bigger in this stage. Now, because the surface cools down, the temperature determines the color. So right now our sun is yellow. If it cools down, it's going to become orange and then red. So this is a very big red star. That's why this stage is called the red giant stage. Red giant stage. So far, the low mass star life cycle starts with the protostar stage, then the main sequence stage, and then the red giant stage. Now, the red giant stage also won't last forever. And that's because as this core gets hotter and hotter and hotter, eventually we're going to get to the point where the core starts to fuse again. It's way harder to fuse helium than it is hydrogen because helium is a bigger element. The bigger the element, the harder it is to fuse. So that helium does not fuse in the red giant stage. But as soon as it gets hot enough, we move into the next stage where the helium in the core is fusing. We still have the hydrogen shell around it fusing, but the helium is now fusing too. So we have two things fusing in this next stage, which is called the horizontal branch. Horizontal branch. I'll show you over here. All right. So low mass star life cycle, protostar, main sequence, red giant, horizontal branch. All right, so the horizontal branch specifically is the stage of a star's life where its core is fusing helium. All right. Now, during the horizontal branch, the core is actually going to grow again. And the reason for that is that if you turn fusion back on in the core, that means it's producing pressure again, and it fights gravity. It's going to beat gravity during this stage. It pushes harder outward than gravity pushes inward. So the core size will grow. If we let the core grow, its temperature will drop because the gas is spreading out. Horizontal branch, the core temperature goes back down. That means, though, that even though we now have two different things that are fusing, because it's fusing at a much lower temperature, it's actually going to produce less light than before. That means that the luminosity will go down as well. Okay. But if you remember, the reason that the surface grew during the red giant stage is because the extra light coming out of the core. If we just lowered the amount of light coming out of the core, that means nothing's pushing the rest of the star out anymore, and it's going to shrink back down almost as small as it was during the main sequence stage. Now, if the surface is shrinking, that means it's getting tighter, it's being squeezed by gravity, and that means its surface temperature will go back up, and the star will stop being red. It will actually look like a slightly bigger version than a main sequence star. All right, now, the next stage of the star. The helium in the core will not fuse forever. Eventually, you'll run out of it. When you do, the thing you make out of fusing helium is carbon and oxygen. So the core in this next stage will be made out of carbon and oxygen. However, you need an extremely high temperature to fuse carbon and oxygen. So notice I did not put a little F in that area. The carbon and oxygen is not fusing. Now, because the carbon and oxygen is not fusing, nothing is fighting gravity down there in that core. So during this stage, the core is going to shrink again. So after the horizontal branch, the core shrinks again. Just like in the red giant stage, that's going to make the temperature go up. But because this core is now shrinking more than ever before, the core is going to get hotter than ever before. And therefore, you're actually going to have two different shells. The hydrogen fusion shell that we still have from the previous stages, but because this inner region is now extra hot, we get to have a helium shell too, right next to the core. So because we now have two shells fusing, and the temperature is higher than ever before, the luminosity is going to go up. So let's write an up arrow in our luminosity column, or row. Now, if we're making more luminosity than ever before, then that means the star is going to puff up larger than ever before. So this star is going to get even bigger than when it was a red dwarf. It's going to get even bigger than when it was a red giant. Blah. Okay. Now, because the star is getting even bigger than ever before, that means its surface is going to get colder than ever before. Whenever you let something spread out, it gets colder. Now, that means, if you notice this, check out these arrows. Now check out the arrows in the red giant stage. Compare these arrows to the red giant stage. They're exactly the same, just more extreme. So this stage is like the red giant stage, but more extreme. Its name is the AGB Giant stage. AGB Giant. So going back over here, the low mass star life cycle is protostar, main sequence, red giant, horizontal branch, AGB Giant. Don't worry about what AGB stands for. Just think of the AGB Giant stage as a more extreme red giant stage. So here's the complete table that we drew. And I want you to notice, you do have to know all of these arrows, but you really only have to remember one stage's arrows, and that's the red giant stages. Because if you look at the arrows from stage to stage, everything that happened here in the red giant stage flipped when we got to the horizontal branch stage. And then it flipped right back to the same direction when we got to the AGB Giant stage. So if you can remember this one, just remember it flips. Also, in every single stage, whatever the core is doing, core size and temperature, the surface always did the opposite thing. So if the core is shrinking and getting hot, the surface is growing and getting cold. If the core is growing and getting cold, the surface is shrinking and getting hot. Finally, if you have a hard time remembering what the luminosity is doing, it always matches the core temperature. If the core gets hot, it's going to make more light. If the core gets cold, it makes less light. Pretty simple. Complicated, but as long as you know the rules, you're okay. Now, the AGB Giant stage is going to mark basically the end of this star's life. The end of the AGB Giant stage is where this type of star dies. Now, the death of this star is a little bit complicated, so you're going to have to bear with me. Now, let's look right here. Remember, in the AGB Giant stage, there are two shells around the core. Now, the helium shell will run out of fuel first because it's hotter the closer you are to the core. So let's imagine that this helium shell runs out of fuel. That means it's going to collapse and get hotter overall. However, remember, when we fuse hydrogen out here, we just make more helium. So as soon as this runs out, the extra temperature will make the hydrogen shell make more helium. When it makes more helium, it refills the helium shell so it can turn back on. When it turns back on, it spreads back out and cools things down because it's spreading out, and that makes it so the hydrogen shell can't make as much helium. Then the helium shell will keep going until it runs out again, and this whole process repeats over and over and over. Long story short, what that means is that at the end of the AGB Giant stage, these shells start to take turns turning on and off, on and off, on and off. Take turns. First the hydrogen, then the helium. First the hydrogen, then the helium. First the hydrogen, then the helium. Now, if these shells turn off and on and off and on and off and on, basically what's happening is that the luminosity will go up and down and up and down and up and down and up and down, meaning that overall the star will start to puff in and out and in and out and in and out and in and out and in and out. That means the star starts to get unstable. Now, it gets so unstable that it starts to release the outer layers of itself. And that's going to look like this. So here, the outer layers of the star have been released from the star. This is how low-mass stars die. Now, if this low-mass star has released its material into space, that means it's released its gas back into, basically the gas of the star has become a cloud again. And we call a cloud of gas in space a nebula. So this star has created a new nebula as it's died. We call this type of nebula a planetary nebula. So the stage after the AGB Giant stage in a low-mass star's life cycle is the Planetary Nebula stage. Now this name is just absolutely terrible. A planetary nebula has nothing to do with planets at all. So this type of nebula was named before we knew what they were exactly, so it has an out-of-date name. Don't be confused, it has nothing to do with planets. Now, after a low-mass star dies this way, the only thing that gets left behind is the core. Now that core is going to be very, very, very small. And because it's very, very, very small, we call it a dwarf. That core also is going to be very, very hot because it was the core of a sun. That's why it's going to have a white color. So we call that leftover dead star a white dwarf. So this is the complete life cycle of low-mass stars. Protostar, main sequence, red giant, horizontal branch, AGB giant, planetary nebula, white dwarf. Now, how big is a white dwarf? Not very big. Here we go. So this is a picture of a white dwarf. Not this. That's a white dwarf. So a white dwarf is literally a very small white star. Now, how big are they in comparison to our sun? They're about 100 times smaller than the sun. They're roughly the size of Earth. So if you look in this picture right here, we have Earth and a white dwarf. However, a white dwarf is much, much, much denser than the Earth. So we'll talk about white dwarfs when we get back to class. End of part 2.